In 1997, NASA sent the first small robot to Mars, about the size of a microwave oven. Since then, we've sent several explorer robots to the Red Planet, each one smarter than the last. These robots have already found things that changed everything we thought about Mars: ancient dry rivers, minerals that only form with water, and even molecules that could mean there was life there billions of years ago. The Perseverance rover, which is there right now while you're watching this video, has already collected rock samples that may hold secrets of ancient Martian life. But here's the most impressive part. The more we discover about Mars, the more it looks like Earth from billions of years ago. Are we looking at our own planet's past? Or maybe at Earth's future? Subscribe to the channel. Leave your like and comment from which part of the world you're watching. Get comfortable and relax. Let's begin. Did you ever wonder how we went from sending tiny robotic scouts to Mars to landing incredibly smart scientific laboratories on its surface? It's a story full of problem-solving, stubborn perseverance, surprising breakthroughs, and a whole lot of firsts. When you look back, it's amazing how, over 27 years, NASA's Mars rovers have gone from something the size of a microwave oven to vehicles that roll around with more tech than your average astronomer's laboratory on Earth. It all started in the late 1990s, and since then, every new rover brings a leap, not just in their own abilities, but in how we even imagine what's possible on Mars in our lifetimes. Let's rewind to where it all began. The Sojourner rover, way back in 1997. The idea was downright audacious at the time. Instead of only gazing at the planet through space telescopes or sending stationary landers, why not drive around the surface and see more? Engineers built Sojourner light and small, so it could be delivered in a tiny lander that bounced to a stop on airbags. Kind of weird, but surprisingly effective on Mars's empty plains. Once the airbags deflated and the ramps unfolded, Sojourner rolled off and took its first slow drive into Martian dust. Now, its main job wasn't finding Martian life or drilling into rocks, but just showing it could roll steadily and send back pictures and data. For almost 3 months, way beyond its official week-long design life, Sojourner trundled around, analyzing rocks and sandy soil. This little robot proved that mobility on Mars was actually possible, setting the stage for everything that would come next. Then came NASA's serious upgrade. Spirit and Opportunity, the twin Mars exploration rovers, which reached Mars in early January 2004. Compared to Sojourner, these two were giants, roughly the size of a golf cart, covered in sophisticated solar panels and packed with cameras and instruments. The mission was already risky, sending 2 identical robots to opposite sides of the planet, hoping at least one would beat the odds. And they both landed in working shape. Each one came with a proper robotic arm loaded with tools for grinding and brushing rocks, plus a high-tech microscope, Moosbauer spectrometer for finding iron minerals, and a panoramic camera that could stitch together stunning images of the Martian horizon. NASA hoped they'd last about 3 months, like Sojourner, but the engineers clearly underestimated the grit of these twin explorers. Now, Spirit landed first in a region called Gusev Crater. Right away, it set to work examining volcanic rocks, rugged hills, and ancient bedrock, finding tantalizing hints that water had at least seeped through the area ages ago. Opportunity, on the other hand, scored a spectacular landing right inside a small impact crater on the other side of the planet, in the area called Meridiani Planum. Within just a few days, Opportunity made its first blockbuster discovery: layered rock outcrops that, when studied up close, clearly formed in liquid water. This single observation was something planetary scientists had been waiting decades for, a case that Mars was once much wetter than we see now. Spirit battled its way across rougher, dustier terrain, breaking its wheels and eventually getting stuck. But even so, It explored the red planet for over 6 years. Opportunity, meanwhile, refused to quit. It kept rolling across the plains for over 14 years, wandering more than 28 miles and setting an off-world driving record. Year after year, both rovers sent home more images, more data, and more stories that revealed a new face of Mars with nearly every sunrise. After a decade of these workhorses, NASA raised the bar by sending the Curiosity rover, which landed in August 2012. Curiosity definitely wasn't shy about making an entrance. Its landing used a never-before-tried sky crane maneuver, lowering the 1-ton rover to the surface on cables swung beneath a rocket platform. This was a huge gamble, but if it worked, it would land a massive vehicle with far more instruments than any previous rover. Luckily, it worked flawlessly. Curiosity rolled out in Gale Crater, a site chosen because it looked like a sediment-rich ancient lakebed, possibly perfect for preserving evidence of past Martian life. What makes Curiosity unique isn't just its size or its nuclear battery that keeps the wheels turning day and night. It's the mobile science lab crammed onto its back. The robotic arm boasted tools for drilling deep into Martian rock, scooping up soil and feeding it into ovens and detectors on board that can sniff for gases, scan for organic molecules, and examine the planet's chemistry on the spot. It includes a laser that vaporizes rock from a distance to analyze their composition, and its cameras can spot details as small as a grain of sand up close. As Curiosity roved around the base of Mount Sharp inside Gale Crater, it discovered ancient riverbeds, found traces of lingering moisture in the soil, and confirmed that Mars once had the right chemistry, water, energy sources, carbon, for supporting simple microbial life billions of years ago. These discoveries didn't just rewrite what we know about Mars, but seriously intensified the search for traces of life beyond Earth. You might imagine there couldn't possibly be much more room for improvement after Curiosity, but then came Perseverance, landing in February 2021. Perseverance is both brawnier and brainier than its older cousin. Like Curiosity, it runs on a nuclear battery, but it's packed with an even wider array of instruments designed not just to study Mars, but to actively hunt for specific clues that life once existed. The chosen landing site, Jezero Crater, has a preserved river delta, a place scientists believe was once a great sheltered lake, perfect for preserving chemical fossils if Martian life ever took hold. Perseverance's kit includes an advanced camera suite, ground-penetrating radar that lets scientists peek a little ways below the surface, spectrometers that can identify organic chemicals right in the dirt, and even a system for collecting and caching rock samples. Maybe the most exciting part of all is its sample caching system. Perseverance is collecting rock cores, sealing them in sterile, cigar-sized tubes, and setting them aside for a future mission. The idea is that, for the first time ever, pieces of Mars drilled and chosen by a rover could be picked up and flown back to Earth in a sample return mission, where labs across the globe can finally analyze them. This is a partnership across years and possibly decades, but the groundwork is happening right now. But Perseverance is not just the ultimate field geologist, it is also a test bed for all sorts of new tech. For the first time, a Mars rover delivered a flying drone called Ingenuity, which made a series of short-powered flights, proving that you can fly in the thin Martian air, a concept NASA had only ever tested in high-rise vacuum chambers back on Earth. The mission even includes MOXIE, an experiment that successfully generated a small amount of oxygen from the carbon dioxide-rich atmosphere, hinting at how astronauts might produce breathable air and rocket fuel on Mars in the future. So, after almost 3 decades, what have we gained from all these upgrades and generational leaps? For starters, speed and endurance. where Sojourner measured travel in feet per day, Spirit and Opportunity pushed a mile marker every few months, and Opportunity ultimately racked up more than 28 Earth miles. Curiosity came next, adding distance plus years of steady productivity thanks to its nuclear power pack. Perseverance, by comparison, comes with artificial intelligence for navigation, so it can plot safer and more efficient routes in real time. Then there's what we're able to measure. Sojourner, born in the 90s, basically confirmed that Martian rocks were, in fact, rocks, and that the terrain could support a robot on wheels. Spirit and Opportunity were true detectives, able to sniff out signs of water, find minerals that need liquid water to form, and, for the first time, reveal the ancient watery landscape. Curiosity could analyze rock chemistry for organics, hunt for basic building blocks of life, check out the weather, sniff the atmosphere for signs of methane, and take ultra-close-up photos of everything from grains of sand to layers of mudstone. Perseverance now is using advanced imaging and rapid data analysis to pinpoint promising rocks for life detection, cache them for future study, and even run live experiments on how we might live sustainably on Mars in the future. What's also striking is how the missions adapted according to what we'd already learned. Sojourner showed that Mars could be explored by robots, so the engineers thought bigger for Spirit and Opportunity. Those two proved Mars wasn't just interesting for its scenery, it had clear geological evidence of past water, and so Curiosity was sent to drill rocks and hunt for life's building blocks. Curiosity's results made clear that a detailed hunt for ancient biosignatures was worth trying, so Perseverance was loaded with tools designed to actually find tiny fossil evidence of life, as well as collect samples that might one day answer those questions for good. In the background, immense challenges had to be solved. Each step along the way saw NASA engineers and scientists learning from past breakdowns, dust storms, stuck wheels, and extreme cold. The batteries went from only solar, vulnerable to dust and darkness, to radioisotope heaters and power packs that keep working through night, storm, and shadow. Rovers got tough about navigation, with Spirit and Opportunity famously able to work around broken wheels and stuck situations, Curiosity gaining advanced driving software, and Perseverance arriving with the ability to steer itself around boulders and dust traps. Communication also changed. The earliest missions had limited bandwidth. Sojourner could only send a handful of photos and science data back through the lander. The later rovers could transmit data first through faster orbiting relay satellites, like the Mars Reconnaissance Orbiter, making high-resolution color panoramas and live science a regular part of updates back to mission control. By now, the Mars Rover program reflects what you might call a living history of exploration and discovery on another world. Each new robot is really a kind of tribute to every lesson, crash, success, surprise, and scientists' late night that came before. You can trace this evolution in every upgrade, every instrument, and every daring problem that gets solved along the way. Spirit and Opportunity, which began as nearly identical, became distinct through their challenges and routes. Curiosity still sends daily weather reports and snaps sunset photos years after landing, and Perseverance continues rolling further, farther, and deeper, carrying the dreams of scientists worldwide who want to know once and for all whether Mars ever hosted life. So when you see a picture of one of these rovers trundling across red dust, examining a lonely rock, or glimpsing the horizon through scattered clouds, remember that those wheels reflect nearly 3 decades of relentless improvement and unwavering wonder. Each rover is an evolving leap, an ongoing story whose next chapter is still being written by every bit of data, every experiment run, and every mile crossed on the silent surface of our planetary neighbor. Among all those miles traveled and every sample snagged from Martian rocks, something pretty mind-blowing started coming together in the data. evidence for ancient water on Mars. This isn't just frames from orbit showing frozen poles or a trickle traced on a hillside. What the rovers have uncovered, beginning with the earliest images from Sojourner and really coming into focus with Opportunity and Curiosity, is a catalogue of telltale clues pointing to a past where Mars actually hosted water that pooled, streamed, and possibly lingered for millions of years. These discoveries are not about the faintest drops or one-off storms. We're talking about rivers, lakes, maybe even seas. Step by step, the pieces started to fit together as the rovers wandered through layered valleys, poked at strange minerals, and took those high-resolution panoramic photographs that started to change scientists' minds about what Mars used to be like. A lot of the excitement first took off in the early 2000s, thanks in a big way to the Opportunity rover and the region where it landed, right in Meridiani Planum, a vast, flat plain chosen partly for its odd reflective signature when viewed from orbit. Opportunity wasn't on the surface long before its cameras spotted bedrock that looked nothing like what anyone was expecting. There were clear, flat layers, almost like pages in a book, and when scientists saw those, they immediately thought of sediment forming and settling out of water over long periods. But as Opportunity got up close, it saw more than layers. Sprinkled throughout the rock were tiny, perfectly round spherules, later nicknamed blueberries. Analysis revealed these were made of hematite, a mineral that nearly always forms in liquid water. Back on Earth, hematite usually develops in lakes or hot springs. The fact that these spherules were just scattered around and sometimes embedded in the rocks made it hard to draw any conclusion, except that these surfaces were once soaked or saturated, and over a lot of time too. Opportunity wasn't just stumbling into speculative clues, it had real science tools aboard. It brought up close instruments to measure rock chemistry, and when it drilled and examined the sediment, it found more signs of minerals like gypsum, which requires water to form, and cross-bedded rock strata that only happen in dynamic environments, such as the bottom of shallow rivers or lakes, where water reshapes the soil over and over again. One of the big smoking guns was when Opportunity examined a spot called Eagle Crater not long after landing and found these fine, wavy layers stacked one on top of another, clear proof of repeated cycles of water rising and falling, depositing minerals as it went. When the rover panned across the horizon, it caught images of ripples and ridges in the soil that looked remarkably like what you'd see at the bottom of a dry lake on Earth. Meanwhile, Spirit was off several thousand miles away in Gusev Crater, a location picked because satellite data hinted that it was an old lake bed maybe filled by an ancient river. For a while, Spirit found mostly volcanic rock, making scientists wonder if the spot had once been covered by eruptions instead of water. But even here, things began to get interesting. Around the Columbia Hills area, Spirit uncovered sulfates and certain salts, including magnesium sulfate and other minerals that form when water evaporates. The concentration of these chemicals, along with findings of opaline silica, often a sign of hot spring activity, made a strong case that water had at least been present episodically, reshaping the rocks through cycles of wetting and drying. But the real heavyweight in the ancient water story turned out to be the Curiosity rover, which arrived at Gale Crater in August 2012. Curiosity's landing site wasn't chosen at random. From space, Gale Crater looked like an enormous impact basin with a mysterious layered mountain, Mount Sharp, rising up in its center. Those layers suggested a long and complex history of sediment buildup, and what's more, some of the features looked like ancient deltas, river channels, and shorelines. As Curiosity began to explore, it found hard proof supporting those hints from orbit. Almost right away, the rover's cameras captured unmistakable signs of an ancient streambed. rounded pebbles cemented together in conglomerate rock. That's not something Mars' thin winds or rare ice storms could create. On Earth, those exact pebble shapes and sizes would mean a river once flowed at a speed you could comfortably wade across if you wore shoes. The roundness of the pebbles said the rocks had tumbled around for ages in moving water, wearing down their edges bit by bit. Digging deeper, Curiosity used its drill to pull out samples from different layers in the rock strata. Lab analyses done with its onboard instruments revealed clays and sulfates, plus traces of elements like sulfur and phosphorus, in the right proportions to say these formed when water lingered and interacted with the ground over a long time. The diversity of minerals was crucial. Some types of clay minerals form only in stable, relatively neutral pH water, which means the water wouldn't have just surged in and then quickly vanished as acid rain or snow, but might have been fairly gentle and long-lasting. One of the thrills for planetary scientists was the confirmation that Mars wasn't only wet in bursts from rare catastrophes or volcano-fueled bursts. It could sustain water in lakes and streams over long stretches, enough to allow life to possibly get started. Another type of powerful clue came from the discovery of mineral veins, white streaks and bands running through Martian rock, which had formed from water flowing through underground cracks and leaving behind minerals like calcium sulfate. Curiosity found these veins in several locations, but most clearly at a site called Yellowknife Bay, where drilling and chemical analysis told scientists that these veins could only exist if mildly salty water once coursed through the fractures. Put simply, ancient Mars saw groundwater moving below the surface, creating veins as that water deposited minerals when it cooled and evaporated. The really interesting thing about all these discoveries is that they didn't come from just one location or era in Martian history. Opportunity found its water signs in wind-blown plains several billion years old. Spirit came across hints around volcanic hills shaped by hot springs and intermittent lakes. Curiosity charted a record of ancient water at the foot of a mountain where river sediments once piled up. Each rover added new evidence from a different geography and a different window in time. This built a kind of overlapping museum of Martian water, showing rivers and deltas, shallow lakes, springs, even the possible cycles of wet and dry that could have happened as the entire planet's climate shifted. Perseverance has picked up this search in a brand new region, Jezero Crater. Researchers chose that crater precisely because satellite images showed what looked like the preserved edge of an ancient river delta, with channels snaking into a fan-shaped pattern. This is the same kind of geology you would see at a place like the Nile Delta on Earth, or where the Mississippi River empties into the Gulf of Mexico. And these places are famously great for trapping and preserving signs of life. As Perseverance rolled around Jezero, it sent back clear color photos of rocks with obvious layers, ridges that probably formed from mud and sand dropped by slow-moving water, and clay minerals that suggest not just a little water, but stable lakes that lasted a while. With a tool set even more advanced than Curiosity's, Perseverance is able to grind into rocks, scan them spectroscopically, and pick out organics and salts that only form in water or in the evaporation that follows. The case for Mars' watery past keeps piling up as researchers combine all this information with what orbiters and landers have picked up from further afield. Beyond river channels and dry deltas, images from satellites and close study of rover data turned up features such as shorelines of ancient lakes, terraces formed as water levels dropped, and broad deposits plainly shaped by erosion and muddy flows. There are even traces of massive floods buried under Mars' rusty dust. Giant channels carved all at once, probably by sudden releases of water, maybe caused by volcanic eruptions melting subsurface ice. These outflow channels, some of them hundreds of kilometers across, point to a planet that was once far more geologically lively and damp than its current frozen deserts would suggest. One important tool in this story has been the identification of certain minerals called phyllosilicates, which include clays. These minerals form as volcanic rock slowly weathers in the presence of water. Curiosity found these in Gale Crater, Perseverance found them at Jezero, and orbiting spacecraft identified them scattered across Mars. What's compelling here is that different clays need specific conditions: neutral or slightly basic water, gentle temperature swings, gradual changes over thousands or even millions of years. You simply do not get huge patches of these minerals without stagnant lakes or rivers with life-friendly chemistry existing for a long time. This conclusion, backed up by the careful remote sensing done by the orbiters, means that the story of ancient water on Mars isn't just about a few wet streaks. It's about a world that could have spent a big part of its early history as a blue planet of its own. As the rovers moved from place to place, they made a habit of cataloging sedimentary structures, things like mud cracks, cross-bedded layers, and fragments of what seemed to be fossilized riverbeds. These are subtle signals that speak to the duration and the stability of ancient water. For example, the presence of mud cracks means you had wet, soft mud that then dried out slowly, which typically only happens on the bottom of shallow lakes with exposed surfaces. Crossbedding means layered sediments deposited by wind, waves, or water that quickly switch directions, as can happen at river deltas or lake shores. Even on a day-to-day basis, both Curiosity and Perseverance keep turning up spots where a close look reveals the grains tumbled into shape by moving streams or the kinds of ripple marks left behind as water moves over sandbanks. A detail that has grabbed a lot of attention over the years is how Mars transitioned from being potentially wet and warm to the arid world we see now. The mineral evidence gathered by the rovers points to this change happening gradually, not in a single catastrophic event. Early Mars, which probably dates to more than 3.5 billion years ago, was warm enough and thick-aired enough that water could exist for stretches on the surface. The older rocks that Curiosity and Perseverance sampled hold onto this story. But as the Martian climate changed, maybe from volcanic gas loss, asteroid strikes, or the weakening of its magnetic shield, the planet lost most of its atmosphere, and the lakes and rivers dried up. This slow loss of water is mirrored in the switch from minerals that need steady water to those that form in only brief salty bursts or derive from frost and dew alone. One of the big uncertainties for a long time was whether this water was there short-term, maybe melted for a brief season by an underground volcano, but then refrozen or gone. The variety and scale of the sedimentary features, though, really support the idea that certain areas, especially river deltas and crater lakes, were sustained for much longer. Some craters, scattered across the Martian highlands, are literally ringed by fossil shorelines, bands of rock and sediment at different heights, showing where lakes or shallow seas slowly dried out, dropping in stages as water evaporated or escaped underground. There are suggestions, even from rover images, that some of these bodies of water persisted for several million years at a stretch, a far cry from the quick floods or snowmelt that dry up in a day. Even in the absence of running water today, clues left behind in Mars geology suggest that the chemical environment could have been right for life. Detected minerals like carbonates and certain clays on ancient lakebeds are important here, because on Earth, these same mineral types preserve traces of basic microbial life forms over the ages. There is no announcement yet of fossils or microbes, not a shred, but finding these environments that were once gentle, watery, and long-lived is a vital first step toward answering bigger questions about life out there. And none of these claims have gone unchallenged by skeptics. Every time a rover finds a patch of clay or a strange deposit of salt, teams on Earth debate intensively whether it really needed water to form or whether unusual Martian chemistry could do the job without liquid present. The case for ancient water has to be supported on several fronts at once. From mineralogy, which says how rocks could only form in water, from geomorphology, which is about landforms shaped by flow and sedimentation, and from the overall patterns seen from orbit, which have to match up with what the rovers actually see on the surface. Over the last 2 decades, the evidence has reached a point where most planetary geologists agree there was a lot of water on Mars, and it stuck around long enough to leave a lasting legacy in the stone. Today, all this detailed ground truth collected by the rovers has a couple of powerful impacts. First, it gives us actual places to focus our search for traces of life. We now know to look in old lakebeds, river deltas, and places chemically altered by groundwater, because on Earth, those are the treasure troves for fossilized microbes. Second, understanding Mars' lost water story gives us a sharper sense of how planets evolve and how climate can shift dramatically over time, which is pretty relevant for understanding Earth's own history as well. Plus, the discovery of past water helped inspire new science targets and future mission priorities, like picking out the best rocks to bring home for deep analysis in real labs. It is a gradual, evidence-driven process that keeps building as every new rover adds more detail. Imagine more sites to drill, more sediment layers to analyze, and chemical signatures to fingerprint. It is not always showy or headline-grabbing, but with each sample and each meter explored, the account of ancient water on Mars grows more convincing and complete. Meeting this challenge, using patient, high-tech detective work instead of speculation, has turned the Red Planet from a place of wandering myths into a world where, billions of years ago, puddles, streams, and lakes quietly shaped a landscape that still holds their memory in every layered rock, mineral vein, and fossilized shoreline. That careful detective work on how Mars was once shaped by water leads straight into another area where the rovers have completely changed what we know about the Red Planet: its weather. Even though people picture Mars as a still, lifeless place, it actually has daily weather, huge seasonal swings, and surprise events like dust storms that can sweep across continents. It is not just about what happened billions of years ago. The Mars rovers let us see what is happening above and around them every hour, every day. The tools on each rover, especially Curiosity and Perseverance, turn out to be as much about monitoring the climate as they are about hunting for rocks or signs of life. As the rovers roll along, they constantly measure air temperature, pressure, radiation, wind direction, humidity, and even tiny changes you wouldn't notice unless you were actually there watching and listening all day long. Take the daily temperature swings, for starters. On Mars, things can get really extreme. Near the equator, right around where Curiosity landed, a typical summer afternoon can have temperatures around 0 degrees Celsius, which is about what you would find on a cold day in Canada. But at night, those same locations might drop to -70 or even -100 Celsius. That is a drop of 70 or more degrees over just 12 hours, way more dramatic than almost anywhere on Earth. This wild swing is mostly because the Martian atmosphere is very thin, less than 1% the thickness of what we have here at sea level, so it cannot trap heat overnight. The result is that Mars has sun-baked afternoons but bone-chilling, almost cryogenic nights, and this happens every single day. When you start looking at pressure, humidity, and the fine details of the Martian air, things get just as interesting. The air up there is almost all carbon dioxide, about 95%, with a little nitrogen and argon making up most of the rest. water vapor and oxygen are barely present at all, usually less than 0.1%. Curiosity's and Perseverance's weather sensors can pick up these tiny traces of water, and sometimes, if the conditions are just right, you get frost forming on rocks in the early morning. Even though it is too dry for rain or snow that lasts, there are brief moments each year when thin, misty clouds will form, made of either water ice or, at the coldest times, carbon dioxide frost, literally dry ice clouds floating across the sky. Winds on Mars are something the engineers worry about a lot, but they also turn out to be key for the planet's whole appearance. The rovers have wind sensors sticking out like tiny flagpoles to catch the speed and direction. On a normal day, winds might blow between 10 and 20 kilometers per hour, but there are times, especially during the big dust storm season, when gusts can go much higher. The effect of all this, the surface gets constantly sandblasted, and you sometimes see dust devils, miniature tornadoes, sweeping across the flat plains. These aren't like tornadoes on Earth. They might be just a few feet across, but on Mars, they can be kilometers high and leave behind dark tracks. Both Opportunity and Curiosity managed to catch dozens of these in action, stitching together images and even time-lapse videos showing dust devils twisting through the landscape. Opportunity actually benefited from these dust devils cleaning dirt off its solar panels, which sometimes saved the mission from shutting down completely when power levels got low. The most famous weather phenomenon on Mars, though, has to be the planet's epic dust storms. Sometimes, local storms pop up in a crater, swirling for a day or two and then fading away. But about every 3 to 4 Martian years, which is equal to about 7 or 8 Earth years, something much larger happens. A massive, planet-encircling dust storm can form. The first sign might be a faint yellow haze captured by a rover's camera. Then the sun starts looking weaker until, after several days, the sky turns mustard yellow or even brown all around. Temperatures can temporarily rise by a few degrees because the dust absorbs sunlight, but paradoxically, the ground below can actually get colder once the thick dust blocks the sun for weeks on end. When these storms get big, they can last months. In fact, Opportunity's marathon mission ended in June of 2018, not because of hardware failure, but after a gigantic dust storm blocked out solar energy for weeks and the rover could not recharge. Martian dust itself is fine, about the consistency of talcum powder, and it is everywhere. The sensors on the rovers monitor how much dust is in the air by tracking the optical depth, which is basically how much sunlight gets through. They also study how the dust settles and gets picked up again, helping scientists figure out which areas get scoured clean and which end up buried over time. The texture and stickiness of Martian dust, recorded by all the rover wheels and experiments, is one reason why Mars exploration is so technically challenging. It gets into everything, clings to lenses and solar panels, and grinds down metal parts faster than you'd expect. The seasons on Mars are marked by much more than just changing temperatures. Because the planet's tilt is almost the same as Earth's, Mars has 4 seasons too, and rover readings clearly track them. During northern summer, the North Pole's ice cap, made of water ice mixed with frozen carbon dioxide, shrinks dramatically. As summer wanes, the heat drops away fast and carbon dioxide starts freezing out of the air onto the ground, especially near the poles. This swapping of carbon dioxide in and out of the atmosphere causes noticeable swings in air pressure, which have been measured directly by Curiosity's pressure sensors for over a decade now. Each Martian year, you can see the pressure in Gale Crater slowly rise and fall in step with the advancing and retreating of the polar frost. Clouds do form on Mars, and the rovers catch them in action. Most are wispy and high, made of tiny ice crystals, rather than fat rain clouds. Sometimes you get a surprise as the sun rises or sets. Curiosity has recorded moments when the horizon glows a bluish pink and thin clouds scatter the sunlight in patterns not seen anywhere else in the solar system. Perseverance, carrying sharper cameras, captured time-lapse videos of clouds drifting by, sometimes coiling in wave-like shapes as they interact with craters and hills. Fog can also hug the surface before dawn, especially near valleys and low areas. The special humidity and temperature sensors designed for this very dry environment passed real-world tests by showing that thin layers of fog or dew will sometimes appear and then vanish as the sun comes up. While this moisture is nowhere near enough to fill a riverbank, it does hint at local weather cycles like the kind astronomers never expected on such a barren world. Radiation, while not a weather in the usual sense, is something that the Mars rovers monitor closely, and it plays a role in how the Martian atmosphere evolves too. Without a thick magnetic field like Earth's, Mars lets in a lot more ultraviolet light from the sun and is constantly bombarded by cosmic rays from deep space. Curiosity has the radiation assessment detector, which measures just how much radiation hits the surface, not just once in a while, but constantly and across all Martian seasons. That's important, not just for future astronauts, but for understanding any signs of life in the soil or rocks. Sunlight, especially ultraviolet radiation, quickly destroys organic molecules on the surface, so knowing exactly how and when radiation spikes or fades during dust storms helps predict where to look for stuff that might have survived underground. Regional weather on Mars is not quite as predictable as what you see on Earth. For example, certain spots regularly form frost at night, but just a few dozen kilometers away, that never happens. The shape of the land, ancient craters, valleys, and even the edges of dust fields can turn into local weather traps, where air cools faster and moisture or dust settles out differently. Both older and newer rovers help map these microclimates by crossing boundaries from one terrain type to the next and logging every small shift with their instruments. What the rovers have collected in daily logs is more than just simple weather reports. Opportunity, Spirit, Curiosity, and Perseverance all measured sudden pressure drops when dust devils passed by, tracked gusts that shaped the sand into new ripples, and watched for seasonal changes that meant more or less sunlight hitting their solar panels. In some cases, they even detected the faintest electrical discharges during dust events, a phenomenon on Mars not unlike static electricity, though much less intense than a thunderstorm lightning bolt on Earth. This constant record-keeping gives scientists on Earth not just a snapshot, but a year-by-year, even hour-by-hour look at Martian weather. They build climate models from this data, improving predictions for how Martian atmosphere and dust cycles actually work, and even test ideas about how Mars might have looked in the past when it had more air and more liquid water. Every bit of this matters for future exploration plans. Knowing when and where dust storms start, how temperatures swing, and what regions get the worst radiation all feeds into figuring out how to keep robots, and one day humans, alive and working on Mars for long periods. Another unique thing about Martian weather is that it sometimes surprises the rovers and the teams on Earth. When the Perseverance rover landed in Jezero crater, nobody expected very many clouds or weather events because the area is usually dry. But not long after arrival, the rover's cameras caught trails of thin clouds, and weather sensors quickly recorded sudden swings in temperature and small gusts blowing through the river delta region. This prompted a round of remote sensing from multiple orbiters, all of them tracking how local winds work in the crater, confirming that even in areas thought to be boring, Martian weather is full of surprises. Martian weather data collected by the rovers has made a big impact beyond Mars itself. One example is how information about dust storms and wind patterns directly helps mission controllers on Earth plan safe landings. Knowing that a region is prone to high afternoon winds or gets frequent morning frost lets engineers tweak their landing systems, parachute timing, and even the sequence in which scientific instruments deploy after landing. These details often make the difference between successfully landing a billion-dollar robot or having it topple in a sudden gust. Wind patterns spotted by the rovers help explain the odd shapes and paths of sand dunes, dust streaks, and rock arrangements seen all across Mars. Over time, as the rover's cameras record moving sand and drifting dust, scientists learn about how fast sand is moving, how stable a location is, and where dust might be hiding things of scientific value under a blanket of powder. The data also helps test ideas about how Mars lost its ancient atmosphere, since the movement of dust and gases might have contributed to the thinning of the air over millions of years. Mars also offers a kind of weather laboratory for studying climate change. Because conditions shift quickly from hot to cold and from dusty to clear, sometimes over just a few months, scientists can use the data to see how atmospheric changes affect everything from soil chemistry to radiation levels. When a big dust storm rolls in and blocks sunlight, Curiosity and Perseverance report the sudden drop in power for their solar-powered cousins, but they also register changes in surface temperature and shifts in how much ultraviolet radiation hits the ground. The whole planet acts like a giant field experiment, one we can watch minute by minute thanks to the rover's instrumentation. With all this data, the models of the Martian climate get updated constantly. The best predictions for future rover or human missions depend on understanding every detail: what time of day dust will be thickest, how temperature changes across different terrains, where a sudden wind gust might threaten equipment, and how clouds or fog could block solar panels or confuse navigation systems. These predictions protect the multi-million-dollar investments on each rover and help design robots that endure harsh Martian cycles without getting stuck or losing instruments to frost, dust, or extreme temperatures. Keeping rover cameras and sensors clean is actually a weather challenge too. Dust collects, eroding visibility for cameras and blocking sunlight on solar panels. For Opportunity and Spirit, the timing of cleaning events, natural dusting from wind or dust devils, often decided whether a rover kept working or slowly shut down as its energy faded. For nuclear-powered rovers like Curiosity and Perseverance, dust still matters for maintaining instrument accuracy and thermal balance, so mission engineers factor daily and seasonal forecasts into their routines. There are even efforts to use the rover's weather data to understand volcanic history. Sometimes the dust storms carry unusual chemical traces, things like perchlorates, a kind of salt left over from ancient volcanic eruptions. Tracking how and where these chemicals spread gives clues to what happened on Mars back when it was much more geologically active. Even without a volcano erupting now, the after effects appear in the way weather systems transport dust and salts from one region to another. Through all these measurements, Mars is not just some ancient desert. It is a place with its own complex climate, acting according to rules that sometimes look familiar, but often turn up surprises. From the thin carbon dioxide-heavy air to wildly fluctuating temperatures, from weird blue sunsets to dust devils towering higher than any on Earth, the story of Martian weather is always unfolding. The rovers, with their steady logging of every gust, frost, storm, and clear day, provide not just data, but daily proof that Mars remains active from one hour to the next. The constant monitoring shapes the way future missions get built and how scientists picture the planet's past, present, and ongoing changes. Every insight from these traveling weather stations continues to reveal just how lively the Martian atmosphere still is, despite its thin air, and what it will take to unlock the planet's deeper secrets. All those observations from the rovers, whether it's changes in clouds or the effects of dust storms, feed right into one of the main reasons that NASA sent these robots in the first place: to find out if life could ever have started on Mars. This question is not just about staring at rocks or testing the air. It's about looking for specific chemical clues, things like organic molecules or patterns in the soil's chemistry, that might show whether Mars was ever home to something living, even if it was just microbes. The modern Mars rovers have taken this search to a much higher level than ever before, thanks to their onboard laboratories and advanced sensors. The big step forward came when the Curiosity rover landed in Gale Crater in August of 2012. That rover was equipped with a sophisticated instrument called SAM, which stands for Sample Analysis at Mars. It works like a mini science lab, able to heat up soil and rock samples, analyze the gases they give off, and check for carbon-containing compounds that are the foundation of all living things as we know them. Early in its mission, Curiosity drilled into ancient mudstone and discovered complex organic molecules buried just a few centimeters underground. These molecules include things like thiophenies, benzene, toluene, and small carbon chains. Now, none of these are proof of life on their own. They can be created by non-living chemical processes too, but their presence is still a huge deal because they mean Mars holds on to the raw materials that, on Earth, are essential for life. On top of these basic organic molecules, Curiosity also found patterns in their distribution that hint at ancient Martian chemistry being a bit more active than previously suspected. For instance, the concentration of organics inside the mudstone was much higher than on the surface, probably because surface layers get bombarded by cosmic radiation that breaks down organics over millions of years. This makes sense, as Mars, without a strong magnetic field or thick atmosphere, lets a lot of solar and cosmic radiation reach its surface, basically blasting away delicate chemicals unless they're sheltered underground or inside rocks. That is why the most meaningful organic finds come from rock drilled just beneath the surface, where they had the best chance to survive across those vast Martian ages. Curiosity's data went even further when its sensors picked up seasonal fluctuations in methane gas in the atmosphere above Gale Crater. On Earth, methane is produced by both geological processes and living organisms, so its presence always lifts eyebrows in the science community. The values on Mars are tiny, parts per billion by volume, so very, very little. But they change through the Martian year, peaking in the northern summer and dropping away at other times. There is still debate about what causes this variation, whether it is sunlight breaking down underground chemicals or gently seeping methane from ancient hydrothermal activity, or something even more unexpected. No one can call this proof of life by any stretch, but all these observations push the scientific teams to keep testing and not jump to conclusions. Meanwhile, Perseverance, since landing in February of 2021, has come with even more advanced tools designed specifically to hunt for biosignatures, which are scientific markers that often indicate living processes. Perseverance has the PXL and Sherlock instruments. These scan rocks and soil for organic materials and map their distribution at a microscale. This lets researchers spot, for example, a clump of organics inside a rock vein next to certain salts or minerals that, on Earth, would favor life or help preserve it. If you find organic molecules clustered together in patterns that match how living communities might organize themselves, like a patch of microbe fossils tightly associated with certain crystal shapes, that is the sort of evidence that, while still not a smoking gun, narrows down the possibilities in a way pure geology can't. Jezero Crater, Perseverance's home turf, is especially promising for these searches. This area once contained an ancient lake with a clear river delta and layers of clay that tend to trap and preserve organics much better than rocky plains or highland plateaus. As Perseverance explores, it picks out rocks that look good for preserving biosignatures, drills tiny cores, and stores them in sealed sample tubes. These samples, if everything goes to plan, could be returned to Earth on a future mission, giving laboratories here the chance to run even more detailed tests, such as looking for specific isotopic ratios or microstructures that would be almost impossible to fake without some type of past biology. The search for organic molecules on Mars also means dealing with the challenge of contamination. Every rover has been carefully cleaned before launch to minimize carrying Earth life or chemicals with it. Scientists use blank sample tubes and repeated tests to track any process that might give a false signal. The team checks and double-checks any findings of organics to make sure they are genuinely Martian, not the result of something left over from the spacecraft. It isn't just about isolated organic molecules, though. The way these chemicals are locked up with certain minerals tells scientists about what kind of water chemistry happened in the past and what types of environments might have been most habitable. For example, clays and certain salts can trap organics for billions of years, while other rocks might actually destroy them. When Curiosity and Perseverance map out where they find clays, sulfates, or carbonate minerals, and at the same time spot associated organics, it is a strong indication that the ancient Martian environment had places where life could have survived, or, at the very least, where its chemical traces could be protected for the future. Even with all these results, the big question about actual life remains open. The rovers have not found fossilized bacteria or anything like a direct remnant of biology, but what has emerged is proof that Mars has held the ingredients for life and kept them safe in spots shielded from harsh radiation and rough winds for billions of years. At the same time, geochemical findings suggest Mars shifted from a more life-friendly environment to a much harsher one, possibly much earlier than Earth, shutting down chances for complex biology to evolve further. Finding signs of past life isn't just about organics or methane. Scientists have also been looking closely at geochemical redox gradients, which is a fancy way to talk about how energy moves in the Martian soil. Living things need energy, and on Earth, the sharp chemical transitions in soils and sediments, where, for example, you have a mix of oxidized and non-oxidized iron, are exactly the sort of places where microbes thrive. Curiosity has measured sulfur, iron, and other elements in ratios that suggest shifting chemical energy sources in the Martian past. These small-scale chemical habitats might be the kinds that would allow life to at least eke out an existence, even if it was never able to flourish across vast stretches of the planet. Another remarkable effort has been the careful analysis of carbon isotopes. When Perseverance takes a rock sample that contains carbon, the science team looks for isotopic signatures, basically the ratio of one type of carbon to another. Certain patterns can hint that the carbon was once part of a living organism. On Earth, microbes often prefer one type of carbon isotope over others. Earlier Curiosity findings have already revealed some strange carbon isotope ratios in Gale crater deposits, although scientists are quick to point out that purely geological processes could also explain them. Nevertheless, chasing down these clues is a main reason for sending Martian rocks back home for lab analysis, since Earth laboratories can achieve much more precise readings than what fits aboard a rover. There's also a lot of detective work needed to decide whether any organic molecules have been changed since they formed, or if they have been preserved pretty much as they were billions of years ago. If the molecules are very simple or have signatures that match what you'd expect from volcanic activity or other non-biological sources, then scientists will want to find more evidence before arguing for life. But if the organics are long, complex, or show breakdown patterns only found when microbes process carbon, that gets more interesting. That's why every new core sample the rovers drill is scrutinized in a lot of different ways, including heating, chemical washes, and scan after scan, from ultraviolet light to neutron bombardment. Sometimes it is not about what the rovers find, but where they find it. Key discoveries include organics and possible biosignatures in places that clearly had water, such as ancient lakebeds, delta deposits, or mudstones that date to warmer and wetter Martian periods. Meanwhile, when a rover checks an especially dry, radiation-baked plain and finds almost nothing, that's another useful data point, showing that conditions were probably never good for preserving anything delicate there. Each piece fits into a map, helping future missions target those Goldilocks zones where the chemistry, mineralogy, and past environmental conditions stacked all the odds in favor of preservation. Beyond organics, one of the goals is to find chemical structures shaped in a way that only life could arrange them. On Earth, most natural organics are pretty random. You won't see repeating patterns or very large, highly ordered molecules unless you're looking at something alive or something made by life in the past. Martian rovers have only scratched the surface here, but advanced techniques like Raman spectroscopy and mass spectrometry occasionally turn up odd signals that require a lot of analysis to interpret. In the end, the scientific community remains careful, avoiding any jump to conclusions until all possible non-biological explanations can be ruled out. The search for life is really a slow build-up of case after case, not a single dramatic reveal. Over the last decade, each time curiosity or perseverance finds organic molecules, odd sulfur or iron ratios, or a patch of minerals formed in water, the teams on Earth use this information to refine their next search. Is there a certain type of rock that preserves organics best? Does a location near an old river delta show a richer soup of chemicals than a volcanic plain? Every answer shapes the design and focus of the next instrument, the next sample, and the future plans for where to dig, drill, and analyze. Bringing samples back to Earth remains the goal with the biggest potential. There is only so much chemistry a robot the size of a car can do with a laboratory that fits on a payload the size of a microwave oven. The hope is that within the next 10 or 15 years, the first Martian soil and rock tubes will arrive at Earth for much more detailed study, including techniques that could spot individual fossilized cells, or even, in the best-case scenario, pieces of ancient biological tissue. The search will then go far beyond isolated molecules, getting into textures, mineral hosts, and the pattern of how chemicals lock together in a way that, in the past, might have belonged to a long-vanished microbe colony. At the same time, it's clear from all these missions that simple detection is not enough. Context is everything. When curiosity finds organics, it's not just whether they are present, but what other minerals are around, what sort of rock held the sample, and what age the sediment comes from. All this builds up a bigger picture of the Martian environment and whether it really could have hosted simple organisms for more than just a brief moment in time. Where this leaves us, after a decade of perseverance and curiosity, is with a planet that, while not yet yielding a yes or no about life, is far more interesting than it looked from telescope images alone. Mars has all the right ingredients. It keeps those ingredients protected in places that are not just rare points, but whole categories of environments, lakebeds, deltas, ancient clays, waiting for more detailed checks. The search for life, at this stage, is about building better tools, refining techniques, learning from each test, and slowly narrowing the field of places where yes might at last become possible. Each rover, with every drill and every sample, adds another layer to this complicated but fascinating story about what Mars was and maybe, just possibly, about what it was home to in the very ancient past. Because every time science teams study these preserved Martian sediments and the chemical fingerprints from ancient wet phases, they're reminded that Mars has an entire variety of landscapes that are nothing short of extraordinary. All the rover missions, from Spirit and Opportunity all the way to Curiosity and Perseverance, have not just wandered across dull flats. They've journeyed through enormous canyons, uneven plains, massive volcanic fields, layered cliffs, wind-carved mesas, and boulder-strewn old crater floors. When you put the findings together, you realize Mars is a planet shaped by more types of geological forces than most people ever imagine. Take, for starters, Valles Marineris. This canyon system stretches over 4,000 kilometers from end to end. That's roughly a quarter of the planet's circumference. If you compared it to something familiar, it dwarfs the Grand Canyon by a long shot, not just in length but also in depth, dropping up to 7 kilometers in some places. Data from orbit showed the canyon's epic size, but cameras on board the rovers and nearby landers have helped fill in the details. Dust accumulates along the shelves, ancient landslides scar the steep walls, and wind patterns shape the sands that drift across the canyon floor. When scientists look at these images, they see signs of past landslides, rock avalanches, and probably even ancient flooding. Over the years, all these observations have led most geologists to believe Valles Marineris wasn't simply etched by water, but mostly by the crust itself stretching and cracking as the planet cooled, maybe with floods rushing through at some stages. The canyon is so significant because it shows Mars went through powerful tectonic changes, and that water may have rushed through when the conditions were right, leaving behind evidence for both dry and wet ages. Next, no conversation about Martian geology is complete without Olympus Mons. It's the largest volcano in the entire solar system. To give you a sense of its scale, this volcano rises 22 kilometers above the surrounding plains and stretches over 600 kilometers across its base. The rover missions never got close enough to drive up its slopes, but high-resolution orbital photos combined with sediment, ash, and lava field samples explored by the robots elsewhere tell us a lot. Olympus Mons is so high that its peak sometimes pokes into the upper atmosphere, meaning frost might occasionally form along its summit. What's remarkable about this volcano is not just its enormous size, but the way the flows built up in very broad, flat layers, each one representing separate eruptions that probably happened millions of years apart. All along the flanks of Olympus Mons, you get debris fans and landslips, showing that the mighty mound is not a static giant. It changes over geologic time, succumbing to small collapses and landslides. Elsewhere on Mars, you spot entire fields of smaller volcanoes, cones, and calderas, especially in regions like Tharsis and Elysium. The fact that so many of these are so well preserved, without much rain or plate tectonics to erode them, tells researchers that Mars once had active magma systems that lasted for hundreds of millions of years. Many rover investigations, especially those that look at the chemistry and texture of igneous rocks, show all sorts of volcanic glass, ash, and crystalline materials spread far from any obvious volcano. This suggests massive eruptions, or even the possibility of super-eruptions that flung material for thousands of kilometers. When Spirit and Opportunity, and even more so Curiosity, studied rock outcrops and layers, they spotted the signatures of volcanic ash mixed in with ancient water-deposited sediments. This means Mars' history isn't just volcanic or just watery, it's cycles of both, sometimes even mixing together. Another stunning feature revealed by the rovers is the network of ancient valleys and dried-up river channels cut through the Martian crust. Orbital images first revealed channels that twisted across hundreds of kilometers, sometimes wide and deep enough to have formed full-blown river systems. When the rovers actually roll into these channels, what they find are telltale sediment deposits, pebble-sized rocks that have been rounded by water, and fine-grained sand layers stacked on top of one another. Curiosity's traverse through Gale Crater, for example, showed clear evidence of ancient riverbeds. Immense piles of conglomerate rocks, gently eroded, hinting that wide streams once flowed for thousands or even millions of years, not just in a single catastrophic event. This has led scientists to suggest that ancient Mars went through different climate epochs where rivers carved out entire valleys before drying up as the planet cooled. Deltas are another part of this story. Perseverance landed at Jezero Crater precisely because from orbit, scientists saw a fossilized river delta there. Up close, the rover's cameras confirmed multi-layered sediment, with each layer representing a new episode of silt and sand being dropped by slow-moving water over the ages. With every drill and core, Perseverance maps out how the sediments get finer, richer in clay, and mixed with limestone or carbonates. These are the kind of settings on Earth that preserve not just sediments, but also potential biosignatures, chemical fossils, or even microfossils if Mars ever had life. The physical scale is only part of the point. The important lesson is that these deltas and sediment fans add detail to Mars' rainfall and hydrologic history, showing not only where water pooled but how it shaped entire regions. All around the planet, other striking geologic features catch the eye. Impact craters of all sizes, old enough that their shapes are softened and floors layered with dust and silt, cliffs rising from the edges of long-dried seas, and rocky mounds where wind erosion has left behind only the toughest minerals. Spirit, for instance, explored the Columbia Hills. These hills turned out to be remnants of older, more weathered terrain, with volcanic ash layers and mineral veins sliced by later water flow. Opportunity crossed shallow craters and ran into the Erebus and Victoria craters, areas that each offered a new cross-section showing the complex history of Mars's surface process, from the initial impact and shock-melted rocks, through aeons of slow weathering to the delicate staining and reshaping by rare Martian winds and dust devils. Layered sedimentary rocks turn out to be among the best time capsules. Curiosity climbs the lower slopes of Mount Sharp inside Gale Crater, which is built of hundreds of meters of stacked flat layers. These form a sort of Martian library of climate changes, preserving the chemistry and grains from different periods, maybe warm and wet, maybe cold and dry, depending on what was happening up in the Martian sky at the time. Every time sample drills or brushes the rocks in these layers, it collects traces of sulfur, iron, magnesium, all within different patterns and concentrations. This record shows that physical conditions shifted over millions and billions of years, a fact confirmed by similar layered rocks catalogued by Perseverance and Opportunity in their separate regions. One of the real surprises came with the discovery of cross-cutting faults and fractures. On Mars, there are places where rock layers are sliced open, sheared sideways, or tipped at odd angles. These features prove Mars experienced stresses from below, probably when massive magma plumes rose or when huge impacts elsewhere sent shockwaves through the crust. Sometimes groundwater later seeped through the cracks, leaving veins of minerals like gypsum or even new types of salt. Opportunity and Curiosity both found these mineral veins, and analysis showed the water that created them wasn't just present once, it sometimes moved and returned in cycles as the chemistry shifted over time. There's a completely different kind of landscape that doesn't get as much attention: Mars's wind-sculpted deserts and vast dune fields. The planet's thin atmosphere means winds can whip up fine sand, carrying it for miles, creating dunes that look exotic and sometimes bizarre. Curiosity and perseverance both rolled through parts of active dunes. They tested how the surface texture changes, how fine particles migrate day by day, and how larger rocks get sorted. Some crater rims have huge dune fields where the grains are sorted more precisely than on any beach. Photographs taken by the rovers show these rippled fields, with dunes up to several stories high, sometimes wandering over ancient sediment layers, masking what's below. The dunes can shift from year to year, their paths recorded in tracks that orbiters can pick out by comparing images over the decades. These same winds also destroy and expose layers, eroding weak rock while leaving harder, more resistant parts standing as pillars or buttes. Another detail revealed by the rovers is the presence of chemical diversity, not just visible features. There are places where the surface is rich in hematite, others where silicates dominate, and yet others where salt-rich layers cut across volcanic rock. The Opportunity rover's discovery of those famous blueberries made from hematite spheres happened in regions where ancient water and volcanic conditions overlapped. The fact that Spirit found opaline silica deposits in a spot most scientists thought was just volcanic shows that hot water and minerals once mixed, leaving behind a record that looked more like a hot spring or hydrothermal vent than a dry rock field. Seismic activity on Mars, although not measured directly by the traditional seismometers we use on Earth, has been hinted at by observing cracks, landslides, and disrupted sediments. These clues let scientists piece together a timeline of when Mars was geologically restless and when it quieted down. Mars, lacking plate tectonics like Earth, doesn't recycle its crust, so many old features linger at the surface, weathered but still recognizable. Every rover snaps and drives through these regions means we gather a bit more of that story. When was Volcano X last active? When did the big outflow channel Y form? How long did wind erosion or water last in Spot Z? Let's not skip the evidence for ancient glaciers. There are landforms at mid and polar latitudes, wide, grooved valleys, and mounds of layered ice that reveal Mars once had thick glaciers. In some places, what looks like simple rock is actually a dusty skin covering deeply buried, ancient ice. Rovers can't drill this deep, but their ground-penetrating radar and the close-up surface observations help spot how ice shapes the landscape, sometimes leaving boulders in strange lines or scraping shallow troughs. Mars also has some huge, chaotic terrain, places where the land looks shredded and blocky, as if the surface collapsed all at once. These areas are often at the ends of the great outflow channels, and geological detective work suggests they formed when underground ice suddenly melted or escaped, dropping the ground above and leaving behind a mess of towers, ridges, and randomly jumbled blocks. No rover has crossed into the center of this terrain yet, but images from landers and orbiters along with soil chemistry samples let scientists build digital models to predict what sort of rock and mineral combinations you'd find up close. Bear in mind that all these physical details from the rovers are backed up by direct measurements every single day. The robots send back not just stunning pictures, but also ratio counts of iron, silicon, magnesium, and sulfur in the ground, radar echoes that tell the difference between rock and buried ice, microscopic images that show how grains in the sand still carry edges sanded down by years of wind or water. The variability in all these measurements is crucial. Mars isn't one kind of planet, and the ground underneath every rover's track is a blend of volcanic, sedimentary, impact, and wind-shaped materials, sometimes all in the same outcrop. What makes Mars exciting for geology is really this patchwork effect. You have gigantic volcanoes sitting next to ancient river valleys, massive, multi-layered craters filled with more recent dust or ice layers, deltas and lake beds tucked away right next to fields of sand dunes, chemical signatures that jump from volcanic to watery to salty, often within walking distance for a rover. There are few places elsewhere in the solar system where you get so much variety, preserved so well over such long timescales. Even now, every kilometer each rover travels adds another set of samples to deepen our understanding. Perseverance, for example, constantly logs the textures and slopes of rock outcrops around Jezero Delta, mapping each new patch of sediment and rock grains to see if they match the predictions about how river deltas should look. Curiosity's slow ascent up Mount Sharp is another step-by-step log of climate, river, and wind-driven processes, catching every subtle shift in mineral type or sediment pattern. So, Mars as a planet is not just a red rocky wasteland. Its surface is this giant visible record of ancient volcanoes, cliff-lined canyons, dried rivers, towering sand dunes, impact-scarred highlands, and hints of frozen glaciers blended in an endless patchwork waiting for every rover to peel back another layer. Every day, the machines trundling across these old landscapes are writing new pages in Mars' geological story. By simply watching, measuring, and sampling, they're showing just how rich and complicated Mars really is, and why every square meter of Martian ground has a new twist worth exploring. This constant stream of new information about Martian rocks and landscapes has set the stage for the most ambitious search NASA has ever run on another planet, actually looking for direct evidence that life might have existed on Mars. This is what the Perseverance rover was purpose-built to do. When Perseverance touched down inside Jezero Crater in February 2021, it wasn't just another vehicle on red soil. It came equipped with a payload of specialized scientific instruments, each one designed to give the most detailed study yet of past environments, organic chemistry, and the microstructures you'd hope to find if Mars ever supported life. The mission's focus is not general geology, but hunting for what scientists call biosignatures. If a biosignature sounds like jargon, it's basically anything that indicates life was once present. Maybe organic molecules arranged in specific ways, microfossil patterns, or even certain chemical recipes that, on Earth, form only because living things are involved. The gamble with Perseverance was landing it in the best possible place to look for these signatures, Jezero Crater. This big impact crater isn't just a random bowl in the ground. From orbit, you can see it once held a wide lake, and a river delta fans out across its western rim, packed with clays and layered sediments. On Earth, places like this are amazing at locking away traces of ancient organisms for billions of years. NASA's idea was that what worked down here might work on Mars too. The technical suite on Perseverance was designed from the ground up for this task. First, there's PIXL, or Planetary Instrument for X-ray Lithochemistry, which gives precise readings of rock chemistry at a tiny scale, mapping out changes in minerals and elements across just millimeters. Then there's Sherlock, which stands for Scanning Habitable Environments, with Raman and luminescence for organics and chemicals. This one uses a kind of ultraviolet laser to spot and map organic compounds and certain minerals that can indicate life-friendly environments. Sherlock's camera can not just see but highlight where organic molecules are enriched in rocks, pointing the team to which cores and samples to pull for deeper analysis. Another special piece is the SuperCam, perched atop its mast, able to fire a laser and spark the surface of rocks from a distance. When this happens, Perseverance collects the light from the sparks and uses that to figure out the chemicals present, sort of a way to scan across tough outcrops before driving over to collect a sample. This ability to standoff analyze means the rover isn't limited to just what sits directly under its wheels. Most important, Perseverance is equipped with the first ever caching system sent beyond Earth. Unlike past rovers, which did all their own experiments on Mars and then just sent data home, Perseverance can drill out small, pristine cores from especially promising rocks. It seals them in titanium tubes and stores them on board, building a cache for potential pickup and return by a future spacecraft. This is a massive leap for science, because what the rover can't finish deciphering on Mars, labs on Earth can finish, using instruments way more sensitive and versatile than anything you can strap to a robot and ship to another planet. The places Perseverance explores in Jezero have been chosen specifically because they might have preserved ancient Martian life, if it ever existed. Scientists guided the rover to the old delta deposits, clay-rich areas and contact zones where groundwater might once have seeped through sediment. The idea is that these places, protected from the worst of the Martian radiation and freeze-thaw cycles, could contain microfossils or chemical traces beneath the surface. The types of biosignatures Perseverance is after include organic molecules arranged in distinct patterns, certain types of minerals formed only by life, or isotopic ratios, the mix between different carbon or sulfur atoms that on Earth tend to show up when biology is involved. What makes this so different from earlier rover missions like Spirit or even Curiosity is the scale and sensitivity of the search. The analyses now go down to the grain, often targeting just a few cubic millimeters in each sample. Take organics, for example. With Sherlock and Pixel working together, Perseverance can scan the surface of a rock, locate a cluster of organic signatures, note the associated minerals, and then drill in exactly the right spot. Early results have shown spots with concentrated organic molecules embedded in layered sediments close to clay and carbonate minerals, very similar to setups known to preserve fossils or chemical traces on Earth for hundreds of millions of years. Every sample Perseverance prepares builds a record not just of what's on the surface, but how signs of life or life-friendly chemistry are linked to past water movement, sediment deposits, and even volcanic episodes. The whole approach is systematic. Scanning, mapping, drilling, and storing samples, not just for today's analysis, but for the much more precise measurements people hope to do once those samples make it to labs back on our own planet. The process has to be methodical because Mars is tough on these kinds of clues. The planet's thin atmosphere and lack of a magnetic field mean high-energy solar and cosmic radiation constantly rain down on the surface, breaking apart organics over time. That radiation only penetrates so deep, a few centimeters at most. So scientists designed Perseverance specifically to drill down past those top layers, aiming for spots where organics and chemical traces might have survived billions of years undisturbed. Perseverance also studies diagenetic processes, how rocks and minerals change over time after they're buried. This matters because chemical signals from biology can sometimes get mixed up or erased as minerals heat up, get shocked by impacts, or interact with Martian groundwater rich in salts or acids. One way to tell if a biosignature is real is to see if it is preserved in a stable environment, protected from the kinds of chemical weathering that strip away organics. Perseverance's sensors help map out whether each sample was locked away in a pleasant setting or stuck in a place prone to breaking down biological clues. Another crucial strategy is looking for diversity. Real biosignatures don't occur randomly. On Earth, you'll often find traces of life clustered around specific environmental transitions, where rivers meet lakes at the boundary of different rock types, or in ancient hydrothermal vents. Printed into Perseverance's mission plan is to seek those same transitions. For example, rover scientists target the fine line where deltaic sediments mix with lake muds, or where clays preserved by wet conditions turn to more acid-rich minerals as the environment dried out. These subtle boundaries are most likely to hold preserved traces, not just isolated chemicals, but patterns, layers, and concentrations which point toward actual living processes having occurred. A lot of attention is given to the possibility of finding microfossils. These are not like dinosaur bones or huge structures, but subtle shapes embedded in rock, sometimes less than 100 microns across. On Mars, any ancient life was probably microscopic and lived in microbial mats or colonies, if it existed at all. The job for Perseverance is to spot textures and chemical gradients in the samples that might match what living mats or biofilms leave behind on Earth. For that, it uses the Watson camera in tandem with Sherlock's spectroscopy, along with ultra-close-up images from distant focal systems. Scientists pore over these images, looking for cell-like bubbles, layered biofilm shapes, or even tube-like structures within mineral veins. It is not all about looking down, though. Perseverance is also checking the nearby surface environment to build up a record of weather and current surface chemistry. There is an entire suite for environmental monitoring called MEDA that tracks temperature, wind, humidity, radiation, and dust. This data lets scientists place each biosignature search in full context. For example, letting them rule out recent contamination or know how deep to drill to get past layers altered by the present Martian surface conditions. Bringing this all together, the core of Perseverance's biosignature hunt relies on three things lining up in each sample. First, you need the right minerals associated with organics, like clays or carbonates with pockets of complex carbon chemistry. Second, you want a physical structure that matches known biological types, like curved layers within rock that look and chemically test like ancient microbial colonies. Third, you need those chemical and physical signals to be stable and undisturbed for a very long time. The more these conditions overlap in a single sample, the stronger the case for what you might call a genuine biosignature. Of course, the scientific teams are highly skeptical by nature. Every discovery is double-checked, looking for abiotic explanations. Ways the rocks could have picked up these organic molecules or strange textures just from geological or chemical activity. No biology needed. There are long lists of what count as false positives, and every strange signal is tested multiple ways against samples collected in different spots and at different depths. Only when the alternatives look slim does the community start hoping they are closing in on real evidence for past life. A big advantage of Perseverance is how it builds a library of connections between what is found on Mars and what is understood from hundreds of years of research into Earth's geology and paleontology. When a Martian sample has a certain shape or cluster of chemicals that in an Earth lab would scream microbe, it is still checked against all known non-living processes. This cross-referencing is important because the chemistry on Mars can be deceptively similar to some biological processes on our own planet, but it's also capable of making some weird bio-like structures through purely non-living reactions. One area where Perseverance is already rewriting textbooks is in mapping the spread of organics across the delta and ancient lake beds. The rover's early results have found more spots with complex carbon compounds than most teams expected. These aren't simple bicycle chain length molecules. Some are branching, some are cyclic, and at least a few hint at chemistry that, on Earth, would be on the road to what cells build. Even so, every compound gets fingerprinted against a library of known geological organics, since ancient volcanic or impact events can sometimes make forms of carbon that mimic biosignatures. Another striking result from Jezero has to do with carbon isotopes. Perseverance is equipped to detect the ratios of carbon-12 to carbon-13 in its samples. On Earth, these ratios often shift when life is involved because living cells process light and heavy carbon differently. The pacing of these isotopic signals across different layers and depths lets researchers piece together how Martian environments changed and whether certain life-friendly signals are matched to times when water was present and pH or acidity levels were suitable for known microbes. It is a lot of small details stacked together, each one making the case only a little stronger until, hopefully, future lab analysis on Earth can deliver the final verdict. The mission isn't just about sitting still and drilling either. Perseverance's route is carefully mapped so the rover can sample at multiple sites: clay layers, edge-of-delta locations, volcanic outcrops, and spots where wind erosion has opened up new views of ancient rocks. Each sample comes with a full record: photo, chemistry, mineralogy, environment, and context, so that when all the data gets put together, the patterns in biosignatures, or their absence, can be traced across the ancient Martian surface. No less important is Perseverance's role in closing the case for habitability. By building up a collection of rocks from various wet, salty, and clay-rich settings, Perseverance lets scientists say more than just life could have existed here. Each time, both the chemistry and mineral evidence point to stable, past water with the right pH and energy sources. The idea that Mars supported habitable environments, at least for microbes, becomes stronger. Mars sample return, the massive team effort planned for the next decade, will rely entirely on Perseverance's stored tubes. The plan is for a future lander and return vehicle to collect the tubes, pack them up, and fly them back to Earth for the kind of deep analysis that could spot even a faint, preserved microbe cell. No robot can match a laboratory on Earth for sensitivity, so the ultimate hope is that Perseverance delivers precisely the right mix of rocks, minerals, and organics, enough to test every possible hypothesis about life on Mars. All this work makes Perseverance a kind of bridge between what machines can learn on Mars and what humans can uncover in remote sensing labs far from the action. Its approach is methodical, slow, and sometimes painstaking, but the results are already broadening our sense of just how complex Mars might have been when the crater lakes and deltas were young. At every new sampling site, the search zeroes in on patterns, clumped organics, fossil-shaped structures, chemical ratios loved by ancient life on Earth, and stacks them side by side with evidence for water, stable chemistry, and unbroken sedimentary layers. So right now, the Perseverance mission is possibly the closest we have come to answering that patient question. Was Mars ever home to life, even at a microbial level? The results so far are promising, and every new sample and scan gets the science community a step closer. For everyone watching back on Earth, the slow, steady build of evidence, chip after chip of Martian rock, scan after scan, layer after layer, reveals a patient, careful effort to pull the most important chapter out of Mars's geological record and maybe, finally, find out whether life ever began there at all. The way Perseverance hunts for signs of past life on Mars is only possible because of decades of problem-solving and inventing new tools. Actually, every rover sent to Mars has forced engineers and scientists to design machines that can do incredible things on their own, survive a world harsher than almost anywhere on Earth, and still send back data for years. Imagine planning a mission that has to operate in freezing cold, deal with intense dust storms, handle rough terrain, and work for years farther from help than anyone has ever gone. That's the baseline for building a Mars rover. Getting just one of these energy-packed science labs safely onto the surface takes years of planning, testing, and working around a never-ending list of problems. Right from the start, just landing on Mars is one of the toughest engineering problems in planetary exploration. The thin atmosphere on Mars, less than 1% the density of Earth's atmosphere, means parachutes alone aren't enough to slow a heavy lander for a safe touchdown. For the Sojourner rover mission in 1997, engineers came up with the concept of airbag landings, allowing the lander to bounce to a stop. By the time Spirit and Opportunity launched in 2003, the airbag system had been expanded and made even tougher since the rovers were much heavier and had to handle more unpredictable surfaces. But for Curiosity, arriving with a whole laboratory on board in 2012, airbags were just not going to cut it anymore. That team invented an entirely new system called the Sky Crane, where rockets lower the rover down on cables for a gentle touchdown. Perseverance updated this approach with advanced hazard avoidance sensors that can automatically spot rocks, slopes, or craters just seconds before landing and guide the craft to a safer spot, something done through computer vision and artificial intelligence routines running in real time. Once a rover is safely on the ground, there are still countless daily dangers to deal with. Mars is not only cold, nights can drop to nearly -140 degrees Celsius. It is extremely dusty, with grains fine enough to get into any exposed crack or electronic connector. For the earlier solar-powered rovers, it quickly became clear that dust buildup could choke off the panel's ability to generate electricity. The solution came from careful positioning, hopes for natural dust-cleaning events from winds and dust devils, and, eventually, a move toward radioisotope power. The Curiosity and Perseverance rovers both run on a plutonium-powered nuclear generator called an MMRTG. It doesn't just supply constant electricity through the wildly cold nights, but it also keeps vital components warm, shielding them from the worst chill. Rover wheels get a special mention because crossing rocky, broken ground year after year is brutal on unmanned vehicles. Early rovers had relatively simple wheels, but after Opportunity's wheels nearly got stuck in deep sand in 2005, and Curiosity's thinner wheels started showing holes after just a couple years, engineers redesigned them. Perseverance landed with wheels made from thicker aluminum and wider treads to distribute weight and handle sharper stones. Each wheel slightly different in design to handle cracks, slopes, or sudden dips. Those wheels also have coded patterns in their shape, which help with traction but also act as a stamp the rover's navigation cameras can pick out, confirming how far it has traveled from photos alone, something important when you can't rely on GPS signals like you do on Earth. Autonomous navigation is another breakthrough, gradually improved from one rover to the next. On earlier missions, human teams on Earth planned out most routes and sent commands every day for just a bit more movement, always with the chance that a wheel might slip into loose sand. Mars is far enough from Earth that radio signals can take from around 3 to 22 minutes to reach the planet, depending on the orbit at the time, so remote driving like you'd do with a toy car just isn't possible. Engineers worked out ways for the rovers to take partial control of their drives. With Curiosity, a system was installed where the rover could scan stereo images, detect possible hazards, and decide on the fly whether to stop, steer around, or even back up and wiggle out of a stuck spot. Perseverance's software is even more advanced, letting it plot its own routes around boulders, choose paths with less risk of slipping or getting stuck, and even identify patterns in sand or gravel that could mean an invisible dip or soft section is ahead. Mars weather is both a worry and an opportunity. Instruments developed for the rovers, such as the weather stations carried by Curiosity and Perseverance, had to be ruggedized to handle massive swings in temperature and work fine with little maintenance. The rover's environmental sensors sit on booms so they can sample real air, but they're also built to shake off dust and survive ice buildup. When dust storms roll in and block out sunlight, or when frost forms on sensor heads in the Martian morning, All those exposed parts have to keep working anyway. Every rover is basically an extreme survivor, but it's also a finely tuned robot. Instruments are miniaturized but packed with capability. For instance, the science labs inside Curiosity and Perseverance carry complex spectrometers, machines that identify chemical elements or molecules by the way they react with different kinds of light or radiation. These devices must be made lightweight, power-efficient, and perfectly sealed against Mars's dust. The drill systems for coring into rocks are another challenge. Engineers had to create drills and sample mechanisms that can handle both soft, crumbly mudstone and hard volcanic rock, all while protecting the precious samples from contamination by modern Mars or anything brought from Earth. One of the most mind-blowing leaps was flying a helicopter on Mars. Ingenuity, which landed with Perseverance in 2021, was designed as a technology experiment to see if powered flight was even possible in an atmosphere that's less than 1% as thick as Earth's. The little drone has 4 carbon fiber rotors spinning about 5 times faster than standard helicopters just to generate enough lift. It weighs about 2 kilograms, talks to Perseverance using a simple radio link, and runs on solar-charged batteries. The tests worked so well that Ingenuity has done many flights, scouting routes, and hazards for the Perseverance team. This one technology demo has now opened the door to using flying robots on Mars in the future, not just for scouting, but potentially for sampling cliffs, caves, or regions that wheeled rovers can't easily reach. Communications with Mars is a whole field of its own. Estimated at distances between around 56 million kilometers and about 400 million kilometers depending on the orbits, transmitting data from the surface back to Earth originally relied on direct links, which were limited and slow. Most modern missions now use orbiters like Mars Odyssey or the Mars Reconnaissance Orbiter as high-bandwidth relays. Rovers send their data up to these satellites, which then shoot high-speed focused signals back to radio dishes on Earth. To make the most of tight bandwidth, engineers developed data compression technologies, prioritized what images or tests to send depending on how much data fit each day, and built in smart routines to send home more in less time. Another innovation has come in materials science. Each component on a rover needs to survive radiation, dust, acid pH, and wild cold. NASA teams developed special alloys, non-stick rubbers for seals, advanced space-rated lubricants for motors, and filters to keep out dust or Martian salts. Even the rover skin, a set of multi-layered shields around electronics and heaters hidden inside instrument compartments, is the result of years of tests. These skins reflect solar heat during the day and retain warmth at night, slowing down the cycles of expansion and contraction that could otherwise crack key parts. Redundancy is a word engineers use constantly. That means backup systems for everything important. If a wheel motor on a rover jams, computers can reroute commands to other wheels. If a drill bit snaps, there's a spare. Most rovers have backup radios and more than one memory channel, so if a cosmic ray zap locks up the primary system, it reboots on the backup without loss of control. Having this redundancy is critical on Mars because no one can just fly up and fix a part. For example, the Curiosity rover's main computer glitched in 2013. The engineers simply switched to the spare and kept the science mission going. Self-repair is something that's still evolving for Martian robots. While rovers don't literally replace broken parts, their software can retreat from damaged wheels, limp along using different wheel combinations, and monitor their own temperature or power to avoid catastrophic shutdowns. In some cases, software updates sent months or years after landing have unlocked new abilities or fixed issues that were impossible to see in testing back on Earth. Perseverance, for instance, received navigation and instrument updates that let it pick smarter drilling targets and refine how samples are handled every time a batch of new mineral types is found. Software isn't just for repairs. Onboard artificial intelligence lets the rover decide what's worth investigating. Perseverance can scan an outcrop, spot changes in color or texture, and decide to take extra images, with a note to engineers back home to look more closely. This is a huge step from the days when every single photo and move needed to be ordered from Earth. One of the underrated challenges is power. Earlier solar rovers, Sojourner, Spirit, Opportunity, were built as lean as possible so they could live off sunlight. These panels had to be perfectly angled, and any dust storm or thick cloud could threaten the mission. Curiosity and Perseverance fixed this problem with nuclear power, but engineers needed to shield the rest of the rover from heat output and plan the entire design around constant energy flow. This shift to radioisotope power sources opened up more mobility, night operation, and safer travel through seasons with less sunlight. But it meant years of partnership with nuclear labs, careful hazard analysis, and political approvals for each launch. Keeping the science gear clean and free from contamination is surprisingly difficult. Every instrument is assembled in ultra-clean labs with strict controls, so Earth bacteria or debris don't hitch a ride and confuse samples. Even with the best precautions, every core sample pulled up by Perseverance is double-checked using reference tubes and careful calibration mixes, letting the science teams know if what they see is truly Martian in origin. Every day, the operations teams must juggle technical surprises with the slow progress of planetary travel. Wheels can get caught on unexpected terrain, temperature sensors ice up, drills get jammed or slip on unexpectedly hard rock. Navigation software sometimes interprets dust shadows as potential hazards. Small communication windows, sometimes only about 8 minutes per day, mean planning builds in hours of wait time for confirmation before proceeding to the next step. One leap forward that came with Perseverance is its complete sample caching, a full system for breaking off cores, sealing them airtight, and stowing them for eventual pickup and transport back to Earth. Building a tiny, ultra-clean lab that reliably moves and packages dozens of samples, even when the robot is buried in dust or battered by wind, was a fresh challenge. NASA's roboticists had to craft components that work after months or years of vibration, cycling, and temperature abuse, and they had to install dozens of sensors to check every joint, tube, and cap against leaks or jams. Ingenuity's success with Mars flights paves the way for more aerial vehicles. Future missions could use bigger drones, maybe even ones that grab samples from cliff faces or provide 3D maps from above to guide landers. The experience with Ingenuity has shown that unexpected wind or temperature changes give important lessons about safe flying, battery management, and real-time camera navigation, opening more routes for exploration. The technical innovations for Mars go well beyond just robotics. They have spun out into improved imaging for medicine, upgrades for Earthbound rovers used in hazardous jobs like mining, and better autonomous control algorithms now being tested on trucks, ships, and planes on our own planet. Each challenge faced and overcome by a Mars mission sharpens technology for work in other extreme environments, from polar research here on Earth to deep-sea drilling or disaster relief in dangerous places. Right now, Mars missions operate within strict limitations, but each rover shows more independence than the previous generation. This trend is set to continue, especially as plans take shape for returning Mars samples to Earth. Handling, sealing, and tracking each bit of Martian rock will rely on what Perseverance and its support vehicles have taught the engineers about durable robotics, software upgrades, and materials that last. Details from every past problem, like Spirit's stuck wheel, Opportunity's dust problems, Curiosity's drill jams, Perseverance's clever navigation, feed back into every future design and the way teams handle the day-to-day pace and surprises of interplanetary work. With every new landing, technical mishap, creative fix, and quiet improvement, NASA has learned that exploring Mars is about more than science. It is an ongoing process of invention, persistence, and turning failures into the stepping stones for bigger discoveries. Rovers today are more rugged, self-sufficient, and smarter than their predecessors thanks to thousands of hours spent solving the kinds of problems you only find by running into them on Mars. That is why the future of Martian science looks more promising with each mission, as engineers grow more capable at overcoming what not long ago seemed impossible. All the innovation that goes into building Mars rovers and pushing them to survive on such a tough planet ends up doing more than just bringing us new gadgets or showing us red rocks. There is something bigger at work in the way these machines are changing how scientists think about Mars and about Earth itself. Because every time the rovers uncover a new detail, be it a fragment of clay, a peculiar rock layer, or patterns left by water, it becomes more obvious that Mars, in its deep past, might not have been all that different from our own planet. For a long time, Mars was imagined just as a dry world, static and dead. But the findings from these rover missions are showing a more dynamic, complex planet, and one that might actually give us a kind of mirror for understanding our earliest history back here on Earth. Take those ancient valleys, riverbeds, and lake deposits revealed by curiosity and perseverance. When geologists study these Martian features up close, they see forms and patterns that are strikingly familiar, channels that meander, deltas that fan out, and sediment layers that speak to repeated cycles of flooding, drought, and slow, steady water movement. The very same geological processes that shape the landscapes we see in places like the Mississippi or Nile River deltas were at work on Mars billions of years ago. The similarity isn't just skin-deep either. Mineral discoveries show that Mars once had liquid water running over its surface and possibly oceans or vast inland seas. Clays, carbonates, and sulfates, all found by the rovers, are minerals that require persistent water and often very specific chemical conditions. These findings challenge the picture of Mars as a planet that was always frozen and hostile. On Earth, these types of minerals and the patterns of their deposition mark the critical places where life first emerged and flourished. So, when curiosity or perseverance drills into those Martian clays or sedimentary rocks, what they are really doing is peeking into a potential time capsule. Researchers use this data to compare with some of the most ancient rocks we have on Earth, those found in Greenland, Canada, Western Australia, and South Africa, places where our own planet's earliest microbial fossils have been discovered. The expectation is not only that Mars might have been Earth-like for its first billion years, but that the chain of events, from volcanic eruptions and thick atmospheres to heavy rainfall, flooding, and eventual drying, occurred in similar stages. There is even evidence for planetary periods. Mars has its Noachian, Hesperian, and Amazonian eras, each defined by big shifts in geology and environment. Earth, in turn, has its Archean, Proterozoic, and Phanerozoic eons. When scientists compare rock samples, chemical ratios, and ancient landforms, they start to see that both planets probably had their own wet youth phases, followed by gradual cooling and drying. Some of the clays drilled by Curiosity, for example, formed around 3.5 to 4 billion years ago, the same era when Earth was covered with shallow seas, forming the first continent-sized land. And in both places, it's the presence of stable water, not just quick floods, that sets the stage for life as we know it. One of the big lessons from these rover missions is how planets hold on to records of change. On Earth, Plate tectonics, erosion, and active geology erase most old features. Mars, by contrast, has kept much of its ancient surface, layer after layer of sediment untouched by rain or continents shifting, sits frozen under dust. Rovers like Spirit, Opportunity, Curiosity, and Perseverance can look straight into history by reading the patterns left in these rocks. Their instruments examine how minerals stack, which elements are present, what isotopes show up, and the precise order of layering, like pages left unturned in a book for billions of years. Finding mineral veins, such as those white gypsum ribbons excavated by Curiosity, offers proof of ancient groundwater. This groundwater plumbing must have moved chemicals and heat through the crust. On Earth, this kind of activity is what kicks off processes leading to hot springs, chemical gardens, and the kind of energy gradients life can tap into. Mars had hot springs too, as seen from silica deposits and chemical maps built by rover measurements. Maybe not as dramatic as Yellowstone, but the same general chemistry. When the Perseverance mission rolled into Jezero crater, it landed near what was once the edge of a lake, where old river channels spill into wide, clay-rich, sediment-filled fans. The rover's high-resolution instruments let scientists compare closely the Martian delta with ancient deltas preserved in Australia and Africa. It's not just about the overall shape. Scientists see the same graded bedding, channels cut by fresh water, and even bathtub ring deposits that are found in old drying lake beds on Earth. By reading these clues, planetary scientists can reconstruct not only what happened on Mars, but also what early oceans and lakes on Earth might have looked like, especially in places where time and geology have erased or deeply buried the originals. All of this becomes especially interesting when you consider the search for ancient life. On Earth, scientists learn to look for microfossils and chemical biosignatures in old clays and evaporite deposits. That's where the oldest evidence of life is found. Tiny microbial mats, chemical gradients, rich carbon signatures. When Mars rovers find clays, carbonates, and those certain types of salty rocks in lake beds, what they are delivering is not just Martian geology. They are serving up planetary habitats almost exactly like the cradles for life on Earth. The fact that Mars' preserved past is still accessible is a powerful reason that returning Martian samples could help solve mysteries not just about Mars, but also about what makes a world truly habitable in the first place. There's another reason Mars turns out to be the perfect analog for early Earth. Our own planet's surface has been thoroughly recycled, which means records older than about 4 billion years are extremely scarce. Only a few places survive where you can find such ancient rocks. On Mars, those records are right at the surface, visible and accessible with the right tools. That allows planetary scientists to check theories about erosion, the cycling of elements, and atmosphere loss without having to dig miles below Earth's surface. In this way, every new rover measurement is a test of our understanding of how air, water, and rock interact to give rise to new planets. Scientists are also learning more about how atmospheres are created and lost. Mars likely started with a thick, wet atmosphere, much like a young Earth. But the planet's smaller size and weaker magnetic field allowed the solar wind to strip much of that air away over time. The data from Martian rock and soil, how much of certain isotopes are left, what patterns show up in salts or sulfates, helps researchers build better models of how volatile elements, like carbon and nitrogen, cycle through a planet's life. Since these cycles are tied to climate stability, rainfall, and even whether water can remain liquid on the surface, they provide new evidence for how early life could or could not thrive. Even Mars' volcanic features have direct links back to our planet's own story. Olympus Mons, the tallest volcano anywhere in the solar system, stands as the kind of feature that Earth might once have built, if not for plate tectonics breaking everything up. Studying these colossal Martian volcanoes helps scientists explain how heat moves deep underground, and by connecting those lessons with data from basalt rocks on Earth, we get a more complete picture of planetary evolution in general. Wind and erosion are other areas where the Mars rover's findings play into Earth science. Curiosity, perseverance, spirit, and opportunity have all crossed fields where sand moves in patterns shaped by global-scale winds and seasonal storms. Maps built from rover data show how dunes grow, shift, and sometimes bury ancient rocks, exactly the sort of dynamics geologists now recognize in the history of Earth's deserts and old sandy riverbeds. Because Mars lacks vegetation to anchor soils or rich biological crusts to lock in sediments, the raw work of atmosphere, particle, and time is often more obvious there, and lets scientists see the bare-bones version of surface change. By closely observing how Mars's surface chemistry varies between volcanic fields, lake beds, river deltas, and dry inland seas, planetary scientists test their understanding of how mineral cycles operate. Sulfates that accumulate when lakes dry, percolates that mark long periods of evaporation, and even the way certain salts trap and preserve organics. These are all processes first worked out on Earth, now being confirmed and refined using rover data from Mars. In practical terms, results from Mars missions end up feeding directly into experiments here on Earth. The search strategies used by Perseverance to hunt for biosignatures in Martian clays began as lessons learned from decades of field geology and microbiology on Earth. Every time new samples or mineral discoveries are made on Mars, there's an almost immediate comparison to the oldest and most primitive rocks from early Earth. This two-worlds approach means new questions and tests are shaped by findings from both planets. Beyond just geology and chemicals, Mars acts as a laboratory for understanding how climate changes through time. Martian layers of dust, silt, and volcanic ash store clues to past wet periods, dry spells, floods, and gradual change. These records are preserved with far less disturbance than on Earth. As rover teams put together year-by-year and era-by-era accounts from Martian ground, climate scientists use the data to run new computer models, asking how temperature, greenhouse gases, and sunlight intensity have driven each planet's history. It's a way of watching, in slow motion, the very cycles that steered the direction of life here and tell us how other worlds might unfold. The discoveries have broader impacts too. As we study Mars, our toolkit for finding life on other planets sharpens, improving not just the hardware but the entire logic behind where and how we look. Every successful mission retraces Earth's own steps, drilling clays, mapping delta fans, running isotope tests that hint at ancient biology. Each time the approach finds something unexpected on Mars, it gives new clues for where to look in the layers of Earth's crust that remain. It even changes the way missions are planned for other bodies, like Europa, Titan, and beyond. Even the main obstacles on Mars reflect our own planet's past challenges. Understanding how Mars' climate and air changed reveals processes that may have happened on Earth very early on. Shifts in greenhouse gases, episodes of global cooling, or periods where high-altitude clouds or volcanic haze tipped the climate in one direction or another. Mars also has rocks formed in acidic water, alkaline water, and everything in between. These direct chemical analogues force scientists to rethink the possible diversity of environments that could have allowed early life to survive and adapt, both there and here. Step by step, the accumulation of knowledge from Mars, built largely from the patient work of the rovers, is coming back full circle. The exploration of a world that, at first glance, seemed so foreign is now producing clues that let us refine nearly every model of our own planet's birth and early years. Desert dust, ancient volcanoes, buried glaciers, retreating lakes, atmospheric leaks. All these elements not only deepen our view of Mars, but connect right back to the engines that shaped life on Earth. Every rover drive, drill, and analysis adds weight to this picture. The more we learn about Mars, the more we come to realize that building a habitable planet is not about a single factor. It's about dozens of interacting conditions that need to line up and persist for millions of years. Stable water, cycling minerals, active geology, and just enough of an atmosphere to hold everything together. When we test these lessons back on Earth's oldest rocks, they keep matching up. So in exploring Mars, we are not just learning about another world's history. With each rover's discovery, whether it is an ancient lakeshore, a clay sequence, or a patch of preserved organics, scientists keep coming back to how closely Mars's history echoes some of the steps Earth once took. The planet stands as a frozen example of what might have been, a kind of parallel run at planetary evolution. As the data continues to come in and our understanding of both planets grows in tandem, the lines between Mars and Earth keep getting clearer and surprisingly often a little closer than anyone expected when the first rover bounced onto the Martian plains all those years ago. So as scientists keep learning how Mars and the early Earth shared some pretty similar environments, the big question naturally turns to what happened to Mars' atmosphere. Because if you look at all that evidence the rovers send back, ancient rivers, layers of clay, minerals that need long periods of water, you can't help but wonder how the planet went from a world that could support liquid water to this cold, dry wasteland with barely any air pressure at all. Figuring out where Mars's thick atmosphere went and how it lost so much over time isn't just an obscure mystery for planetary scientists. It is one of the keys to knowing how long Mars was actually habitable and influences how researchers think about atmospheres on other worlds, including our own. Today, if you stood on the surface with nothing but a standard spacesuit, you would experience atmospheric pressure about 600 pascals, less than 1% of what you feel at sea level on Earth. That is so thin that water boils at temperatures just above freezing, making liquid lakes impossible on the surface in current conditions. But for all those rivers and lakes in the ancient Martian landscape to have existed, Mars must have had a much denser, more protective atmosphere billions of years ago. The search for Mars' missing atmosphere is one of those problems where every rover, lander, and orbiter adds a bit more to the puzzle. Let's start with what the rovers have picked up in terms of direct evidence. Curiosity, Perseverance, and their predecessors analyzed the composition of rock, soil, and even the gas in the atmosphere itself. One of the main signs of how Mars lost its air comes from looking at the isotopes of certain elements like carbon, oxygen, and argon. Isotopes are just versions of an atom that have a different number of neutrons, making them heavier or lighter, and processes like atmospheric escape usually prefer one over the other. When Curiosity samples atmosphere or tests the gas trapped in rocks, the team measures the relative amounts of lighter and heavier isotopes. For example, they look at how much carbon-12 is present versus carbon-13. Or how much argon-36 versus argon-38. It turns out, over and over, that the Martian air and rocks are enriched in the heavier isotopes. This tells scientists that the lighter versions have been escaping into space over billions of years, a solid hint that Mars's upper atmosphere was never able to hold on to its air the way Earth can. That escape is mostly powered by the Sun. Since Mars lost its global magnetic field sometime early in its history, possibly a little over 4 billion years ago, it could no longer protect its atmosphere from the constant stream of charged particles known as the solar wind. This wind, essentially a constant outpouring from the sun, smashes into Mars' upper atmosphere, knocking atoms loose. The result is a process called sputtering, where atoms get enough energy to escape Mars's weak gravity and drift off into space. Over time, this slow but steady leak adds up to a huge loss. Orbital missions like NASA's MAVEN have watched this atmospheric stripping in action today, but the rovers anchor the long-term story. By measuring isotopic ratios in ancient rocks across different terrain types and ages, the surface robots show that atmospheric escape is not something new. It's a process that's been whittling away the Martian sky for billions of years. In addition to this slow atmospheric escape, there may have been dramatic events in the planet's past. Big asteroid impacts, periods of extreme volcanism, and sudden chemical changes, all of which could have triggered massive losses of air. When volcanoes erupt, they can both add new gases and also, in the aftermath, trigger cooling or changes in the chemistry of the air. The evidence from rover missions suggests that Mars was volcanically active for hundreds of millions of years. Curiosity has analyzed sulfur and chlorine in sediment samples, which shows how volcanoes both released and then redistributed gases across the surface, changing the planet's air over and over. At the same time, there's geochemistry. Research with rover data demonstrates that surface rocks on Mars lock down a surprising amount of carbon dioxide and water. In other words, instead of just floating free in the sky, many of those molecules got trapped into the crust over time. On Earth, plate tectonics and weathering keep recycling these gases, but that hasn't happened on Mars in at least several billion years. Perseverance finds minerals like carbonates in rocks laid down in ancient seas or lakes, hinting that Mars' early thick air was partly buried as chemical deposits. Some scientists think this sequestration process might have removed a fair bit of Mars' original greenhouse gases, cooling the planet and thinning the air even faster. Another mechanism that comes up a lot in recent science discussions relies on ultraviolet sunlight. Without a dense ozone layer like the one on Earth, a huge amount of solar ultraviolet smashes into Mars' upper atmosphere. Energy from this UV light breaks apart molecules like carbon dioxide and water vapor, freeing up oxygen and hydrogen atoms. Hydrogen, being exceptionally light, escapes most easily, especially in the thin sky. This is one reason why the Martian atmosphere today contains almost no hydrogen and even less water vapor, while oxygen is mostly locked in oxidized dust and rocks. The Martian dust itself plays a role, as rover instruments confirm. Weather on Mars kicks up vast amounts of dust, and the sunlight it reflects or absorbs helps regulate day-to-day temperatures as well as longer-term climate. During massive dust storms, thin atmospheric water vapor can get temporarily trapped or released, but over hundreds of thousands or millions of years, these cycles probably allowed even more water and certain gases to escape. The rovers have helped track the history of Mars's air and water loss by mapping surface features like ancient shorelines and river deltas. What they reveal is that the wet, warm conditions needed to persist for very long stretches, possibly as much as a few 100 million years, or up to about 1 billion years after Mars formed. That means Mars's protective atmosphere must have stuck around for a while before it was stripped away, vaporized, or locked into chemical form. If you look at the age of rocks the rovers drill into, a picture emerges with 3 big chapters. First, early Mars, more than 4 billion years ago, saw lots of volcanic outgassing, thick air, warmer temperatures, and running water. Over the next several 100 million years, a combination of magnetic field loss, solar wind stripping, big impacts, and slow sequestration into minerals took away most of the air, leaving just a thin shell behind. By the Amazonian era, stretching from about 3 billion years ago to now, Mars had only the faint frigid atmosphere we see today, and no signs of stable, long-term surface water. One amazing find made possible by the rovers was seeing how even tiny pockets of air trapped inside minerals match this whole planet's story. When Curiosity analyzed trapped gases in rock samples, sometimes using its onboard laser or heating tools, it found patterns consistent with ancient air, rich in carbon dioxide and with ratios of noble gases like argon and xenon showing who escaped faster and how quickly atmospheric thinning took place. Besides the scientific details, these findings also affect the search for life on Mars. Since a thick atmosphere helps shield a planet's surface from damaging ultraviolet radiation and stabilizes water and temperature, the timing of its loss matters a lot. If Mars held on to a dense atmosphere and running water long enough, maybe it was home to simple life for millions of years before things became too cold, dry, and barren to support biology. So every bit of isotope data and ancient climate record helps scientists narrow down the exact window when Martian life could have had a chance. Our own planet, as it turns out, also loses atmosphere. But Earth's magnetic field and tectonics keep recycling it much more effectively. Understanding how quickly Mars bled off its air compared to Earth helps scientists make predictions about other planets around other stars, so-called exoplanets. The idea is, if a planet is small, lacks magnetic protection, or is bombarded by a strong solar wind, it is probably in danger of losing its atmosphere fast. From a technical perspective, understanding the fate of Mars's atmosphere is crucial for any future human exploration. Engineers have to design life support, shelter, and vehicles for a place where the air is so thin you need a pressure suit, water evaporates off your skin, and the slightest leak in a habitat could be deadly. That is a big reason NASA and other space agencies invest so much in understanding how Mars' air changed, because it determines everything from habitat design to using Martian resources for air or fuel. The measurements being made today go well beyond the surface. Perseverance, for example, includes MOXIE, a demonstration device that pulls carbon dioxide from the Martian air and turns it into oxygen. Monitoring how much CO2 is available and whether its concentration changes with the seasons not only helps scientists study atmospheric processes, but lays the foundation for astronauts to someday live off the land rather than bring everything from Earth. Figuring out the fate of Mars' atmosphere means building up models for what it would take to thicken the air again or produce enough oxygen for crews and plants. Curiosity's weather and environmental data, mapped over more than 10 Earth years, reveal the year-to-year consistency of the thin air and how local effects, like dust storms or temperature swings, briefly shift the balance of gases. Together with orbiters monitoring the upper atmosphere, the rovers are key in seeing whether any kinds of residual air replenishment are happening, or if the atmosphere remains stubbornly stable and thin. In all this, the story of Mars's missing atmosphere isn't one of a single catastrophe, but mostly slow, persistent processes. Every test with a new rock core, every drill into clay, every analysis of trapped gases, and every record of dust movements fills in another line in the chart that helps scientists reconstruct the shift from a blue planet to a red one. There could be some missing factors still. For example, did Mars ever vent new gases from inside via late volcanism after the main air loss? Did asteroid bombardment late in its history deliver or strip away gases faster than previously thought? Each rover mission gives small but crucial details to help answer that. What comes from all this patient, decades-long work is much better insight not only into Mars' history, but the risks faced by other planets. Since atmosphere is the biggest defense a planet has against space radiation, it sets the clock on when and where life can emerge and last. A thin air means more radiation smashing the surface, faster water loss, and less climate stability. Those same lessons help us understand Earth's past and challenges for its future. Tapping into every measurement from the Martian rovers, humans are gradually putting together a precise story about planetary air and habitability. From isotope ratios and noble gases to daily patterns of CO2 and weather, the whole picture comes together to show just how complicated losing an atmosphere can be. The red planet stands as a reminder that what keeps a world alive is often fragile. A mix of size, magnetic field, volcanic recycling, and distance from the sun. Learning why and how Mars lost its air may not just help us plan missions or dream about terraforming, but could make a serious difference as we keep an eye on our own climate, air, and resources moving forward. The search for Mars' missing atmosphere highlights just how much more we still need to learn about surviving on another planet. All this research, all the technical problem solving, and all the discoveries sent back by the rovers have been quietly building an instruction manual for the next challenge, eventually sending people to Mars. In a way, every wheel that turned, every sample drilled, every wind gust measured, and every system that survived a bitter Martian night or a months-long dust storm was one step toward figuring out what it will really take for humans to live and work safely on the red planet. The biggest lesson that keeps showing up, mission after mission, is how harsh and unpredictable the Martian environment can be. It is cold. Average surface temperatures hover below -60 degrees Celsius, and nights routinely drop much colder. Dust is everywhere. Rovers like Spirit and Opportunity ran on solar panels, so every storm risked choking off power. Teams learned to monitor dust levels day by day and even hoped for Martian cleaning events when strong winds or dust devils blow sand off the panels and give a boost in power. That is why landers like Curiosity and Perseverance shifted to nuclear power, using a radioisotope generator for reliable electricity and warmth. For future astronauts, the lesson is simple. You need backup power, redundancy in life support systems, and ways to handle dust both inside and out. Otherwise, you might get stuck in the shelter with no way to recharge or heat your gear. Temperature swings are hard on equipment, seals, and batteries. The rovers had to handle over 100-degree differences between an afternoon and a night. Materials shrink, stretch, crack, or freeze. All the vital electronics and batteries are packed deep inside thick, insulated warm boxes, and each cable, drive motor, and sensor must be shielded. Habitat designers for human crews are now borrowing those techniques, planning for multi-layer insulation, secondary heaters, and flexible plumbing able to tolerate frost and thawing cycles. Space agencies also study exactly how items like Mars rover wheels or camera lenses wear and degrade, using that real-world data to pick the best materials for spacesuits and tools. The thin atmosphere, with only a fraction of the pressure and almost zero oxygen, means astronauts cannot count on just pumping outside air through a filter or living off the land, at least not easily. But those same conditions make the job of landing on Mars incredibly tough. The rovers showed how parachutes alone will not slow a heavy craft enough, so engineers developed heat shields, retro rockets, and finally, precision-powered sky crane landings like those used for Curiosity and Perseverance. All those landing tests, shock sensors, and computer simulations form the backbone for designing human landers able to reach the surface without slamming into rocks or tipping into a crater. Detailed digital maps built from rover photos, especially where dust drifts or loose soil can trap a vehicle, are now the blueprints for choosing safe places to touch down. Radiation is another hard reality. Mars, having lost its global magnetic field, gets showered in cosmic rays and bursts of solar energy. Both Curiosity and Perseverance carry radiation detectors that measure daily, monthly, and yearly levels of ionizing radiation hitting the Martian surface. This data confirmed that living unshielded on Mars, even for a few months, would put humans well over NASA's lifetime acceptable radiation dose for astronauts. The solution is to build thick-walled shelters, bury habitats under Martian soil, or use purpose-built shielding that takes into account all the micrometeorites and cosmic rays. The design of crew modules and rovers now includes plans for storm shelters, areas with extra water, or polyethylene blocks, drawing on exact exposure profiles gathered by the rovers. By comparing radiation spikes during big solar storms with losses of atmospheric pressure and temperature changes, researchers have worked out which combinations pose the greatest risk, and that experience guides how supply dumps, hibernation modules, and emergency protocols are built. Navigation and mobility are critical as well. Every rover has run into trouble on unexpected terrain. Opportunities near-ending sand trap, Spirit's immobilizing wheel jams, and even Curiosity's slow progress over sharp rocks all taught NASA the importance of real-time hazard detection, strong wheels, and software that notices sand softness or hidden dips. Humans will face even more dramatic risks, because getting out to fix a stuck vehicle may not be an option. Robotic scouts and small autonomous rovers will likely be used for safety checks, route scouting, and cargo dragging, not so differently from how Perseverance works alongside the Ingenuity helicopter for navigation and planning. Robust communications are a must. The rovers transmit their data up to Mars orbiters, which then fire it back to Earth using powerful radio dishes. Mars has windows of high and low signal quality, sometimes allowing only a few megabytes per day. This experience is teaching engineers to store and forward critical information, prioritize what to send, usually health, safety, and status first, then science, and build redundancy so nothing important gets lost in a solar storm or a dropped packet. Future Mars crews will rely on similar orbital relays or satellite constellations, so they never lose touch during a dust storm, polar night, or emergency. Another major lesson from Mars missions is the need for autonomy. Both robotic and human explorers must be able to operate with limited real-time support from Earth. Because communication delays mean even a simple command can take anywhere from about 4 minutes to more than 20 minutes to reach Mars, the rovers had to learn to make independent navigation, sampling, and hazard avoidance decisions. Missions now rely on onboard computers, advanced image recognition, and smart path planning to keep progress steady and minimize risk. These routines are the early test runs for software that will assist astronauts in making fast decisions when there is no time to wait on a call to mission control. Dust is not just a power problem. It plays havoc with moving parts, filters, seals, and clothing. Mars dust is a fine powder, clings to everything, and on top of that includes toxic perchlorates that break down into harmful compounds under solar radiation. The rover's wear and tear, blocked vents, and compromised seals have highlighted the need for airlocks, internal cleaning routines, and suit ports that keep dirt outside living quarters. The search for water on Mars has gone from "is there any" to "how much" and "where" exactly. Rovers have found ice in the ground, seasonal frost, and hydrated minerals deep in the soil. For astronauts, this is key. Water means drinkable reserves, the potential for growing crops, and the ability to make rocket fuel and air. Learning where ice sits, how deep you need to dig, or how to purify groundwater is now one of the main targets for test drills, robotic scouts, and in-situ resource utilization projects. Sample collection and contamination avoidance provide some of the trickiest lessons. Rovers have gone through extraordinary measures to keep their sample instruments and containers free of Earth life or stray molecules. Every tube and drill bit on Perseverance, for example, is double-checked and witnessed by blank control tubes so teams know if any reading is compromised. These protocols are directly shaping how future astronauts will collect, store, and transport both scientific and commercial samples. Whether soil for biology, regolith for making bricks, or ice cores for geology. Techniques include everything from glovebox-like sealed chambers and cleaning cycles to digital chain-of-custody logs and onboard analysis before anything gets packaged for return. Life support is always front of mind because the margin for error is so thin. The rovers taught mission planners to expect the unexpected. On Mars, if your oxygen generator clogs up with dust or a heat exchanger freezes, a delay of even a few hours can be dangerous. This led to the development of multipath redundancy for air, water, and power, as well as sensors that monitor everything from oxygen levels to atmospheric pressure so crews can spot trouble before it snowballs. Inspired by Perseverance's MOXIE experiment, system designers are using electrochemical tech to pull oxygen from the atmosphere, or even to recycle wastewater, carbon dioxide, and organic waste with as little manual intervention as possible. Habitat placement leverages everything the rovers have learned. For instance, wind patterns, nearby ice, dust storm frequency, and sunlight all dictate where a crew shelter should be built to maximize energy, minimize risk, and allow easy access to the resources. Detailed terrain maps made from rover images now serve as context for mission planners, guiding simulations for emergency landings, surface excursions, or escape routes. Robotic repair is another area where rover experience leads the way. When Spirit or Opportunity got stuck, remote teams from Earth brainstormed and tested dozens of virtual escape routines or backup maneuvers. Now, mission scenarios for human teams on Mars include onboard repair robots and smart diagnostic software designed to spot problems, attempt fixes, and provide real-time guidance without waiting for video or expert input from Earth. Food and crop science is borrowing from Mars soil analysis too. Because rover findings show the natural soil is low in nutrients and the presence of perchlorates can be harmful, mission planners know they'll need to bring clean substrate or find ways to treat the Martian soil before planting. Experiments both on the International Space Station and simulated Mars farms on Earth use data from rover chemistry tests to predict what supplements or microbes could turn local dirt into safe, productive growth media. The longevity of Mars missions reveals more subtle needs. Opportunity lasted more than 14 Earth years, far beyond original estimates, even surviving multiple winters and dust storms. This unexpected endurance taught teams to always pack spares, build in hardware and software margins, and expect at least occasional miracle events, like dust devils cleaning solar panels or hardware bouncing back after a deep, cold snap. As NASA moves toward sending astronauts, every rover success and failure is translated into protocols. How to handle forced hibernation, power emergencies, extended communication blackouts, and on-the-fly mission replanning. The partnerships formed for Mars exploration between NASA, universities, international partners, and even private industry have laid groundwork for new types of collaboration. As a Mars crew mission gets closer, engineers, medics, geologists, biologists, and robotics specialists all draw from the School of Hard Knocks created by every Martian rover crew. Schedules, training, risk assessments, equipment lists, and even astronaut selection criteria reflect lessons from real events, like when Opportunity got stuck or Perseverance unexpectedly jammed a drill. Finally, The most important lesson from the rovers is that flexibility, creativity, and steady adaptation are essential for Mars. Every plan must have a backup. Every habitat, vehicle, and suit must withstand unexpected environmental swings, whether a long-duration storm, surprise frost, or strange soil chemistry. This constant learning and updating mindset is now hardwired into mission design for Mars, showing up in software that can be updated from Earth, hardware swappable with tools brought along, and daily operations that always include a margin for the unpredictable. All these years of rover discoveries, hidden ice, dust storms, geology, survival strategies, are directly shaping the first true exploration of another world by humans. Every little setback and workaround becomes a lesson. Teams working on sample curation, engineering, resource production, mobility, robotics, and science are picking through the data logs, reading the lessons, and test driving Mars again and again on computer before anyone sets out for real. In a lot of ways, this careful accumulation of experience is already half the journey. When crews do finally land, thanks to the patient, persistent work of all those rovers, it will be on a planet that's a little less strange and a little more within reach, because every bolt, wire, and experiment sent out there has already lit the path.